Hi everyone, good morning from the UK. Welcome to the 12th Surface Ventures webinar. Before we go any further, as usual, can I get you to please write where you're joining us from today in the chat box on the right-hand side. Great, that seems to be working. A lot of great places there. Okay, so to begin, my name's Tahid Khan. I'm a VP at Surface Ventures and I'm your host for today. We are a non-for-profit organization and our mission is to provide world-class surface engineering education for academia and industry. So every month we bring you a sector-leading speaker to present the current challenges and future trends in surface engineering. So today it's my pleasure to introduce Dr. Mehran Muazzin, who will be talking about mechanical characterization of biological tissues. So a bit of background to Dr. Muazzin. He's an associate professor of biomedical engineering in the Department of Mechanical Engineering at the University College London, UCL. His research is focused on biomechanics of bones and joints, particularly to understand the underlying mechanisms of growth, adaptation, and repair through the use of computational and experimental techniques. His research has been funded by a number of funding bodies and has been published and presented in a number of journals and conferences. So in terms of agenda, we'll start with the presentation and then switch for a few minutes to our sponsor of today, who is Anton Parr, and then we'll come back to our presenter for your questions. We are planning for the session to be around 60 minutes in total. However, depending on the questions, this may go over, so we do apologize if that occurs. There will also be a quick GDPR announcement, as there will be a few brochures available from our sponsor. And if you do download them, someone will get in touch to provide further support. Also, a little reminder of our website, surfaceventures.org. It features videos from our previous talks, information regarding upcoming webinars, and information about the Surface Ventures team. So please do visit. Before we start, we always like to know a little bit about yourselves. So we're going to have a quick poll, which should appear on the screen. And it's a really simple question. Are you from industry or academia? Okay, great. It seems like we've got a strong presence from the academic community. That's great. So now what I'd like to do is hand over to our speaker, Dr. Muazzin. Over to yourself.
Hi, everyone. Thank you, Tohid, for that introduction, and good morning to everyone from London. Hope you are all well and safe, and thank you so much for having me to give this talk on mechanical characterization of biological tissue. So the outline of my talk is going to be basically to give an overview on indentation. I'm not quite sure how familiar you are with this technique, so I'll just try to give a brief overview on the technique. I must say I won't be going in depth into various nitty-gritty of it, but it should be a brief introduction to the technique. I'll then focus majority of my talk on two applications, two areas that we have been focusing on using this technique to characterize craniofacial growth and looking into calcified tissue within the skin. Within these two topics, I try to give you a little bit of background why we have been interested in these areas and what was the story around it, and you will see how indentation has helped us and enabled that research. And then I'll finish. I have one slide basically on some other ongoing work in the group, and I'm sure there are many other examples that is happening. So let me start with a brief overview. Well, indentation is basically pressing a hard tip into a flat surface, and you have a known force, and what you are characterizing is displacement and the contact area as you are pressing this hard tip into the flat surface. And it's effectively enable us to characterize various materials irrespective of their shape, size, and porosity. Obviously, a classical technique that has been widely used is tensile testing. Yeah, I thought I like these images because it kind of put the whole thing in perspective. Two techniques or two systems, the terms that you may come across is nano-indentation and atomic force microscopy. And they are effectively referring into the scale that you are indenting, whether you are indenting at the micro or nano scale, or you are indenting further down at atomic scale. That's I think it's quite clear on the image on the right hand on the left hand side in terms of the displacement that you are applying and the level of load that applying and the different classification between these three different technique, if we shall say. So you are indenting a surface. Well, there are various indenters available broadly. You either have sharp indenters or you have blunt indenters. And spherical indenters are usually used to indent the soft materials. In the case of biological tissue, you can think of soft tissues, whereas sharp indenters, such as Berkovich, are mainly used to indent harder tissues, such as calcified tissues, bone, and so forth. When it comes to the indentation, a key element is sample preparation to prepare a flat surface, and it's rather challenging, and it involves various steps. I kind of grabbed these images to show you one of the samples that you will see later on. So you have a mouse skull on the far left that we have been then potting, and then you can see a section of it on the bottom right through the skull. So it basically really important. Some key parameters here are your sample alignment, because that is effectively going to define the plane that you are indenting your sample. Surface roughness is very important. So you go through different phases of polishing to get a smooth surface. And that is crucial because effectively your indentation depth is to be kind of an order of magnitude over whatever that is your surface roughness. With biological tissues is obviously very important. The hydration and keeping that tissue in its natural status is quite important. So that's another parameter to keep in mind. But anyway, I thought that I just show you that different steps that it involves: fixing your sample, removing air bubble from your resin, pressurizing the resin, then cutting it and polishing it, polishing your sample to the roughness that it's appropriate for your work. Once your sample is ready, then your next step is the indentation, obviously. And I just grabbed this image from a nice review paper by Professor Zizet. And P is basically load, H is displacement, and T is time. And you can see different plots of load over time. The green line is just basically, you can see that you have a loading phase. Then you have a hold phase in this case, and then an unloading phase. And if you then look at force versus displacement, then you have the red curve, and you can see the loading, hold time, and unloading, and so forth. And effectively, we are trying to estimate the hardness, the elastic modulus, the material that we are interested in from these graphs that you can see here. There are different methods, different approaches to characterize the graphs that I just showed you. Some of these approaches are taking into account the elastoplastic deformation that happens. Some take into account the viscoelastic properties, and other approaches are taking into account the viscoelastic plastic deformations. And throughout most commercial systems are using basically Oliver Farr method, which is effectively extracting the properties of the material from the elastoplastic properties. And throughout the talk, that's the method that has been used in the examples that I'll be giving you. That's the method that we have used, and it's, as I said, it's used by most commercial systems. I thought that given that the indentation is heavily relies on fundamentals of contact mechanics, I haven't done justice if I then give you a little overview of the basics of contact mechanics. And Hertz basically found this relationship when you're pressing a hard object into a flat surface between the different components here. I mean, you can see a hard object. I'm not sure if you can see my mouse, but you have a hard object pressing against a flat surface with a radius of Ri, and the indentation, let's say depth is HT, and you can see various parameters there. And he basically found that these relationships exist between various parameters that you can see on the screen. And this was basically the foundation for the whole technique. And many people went on to then describe and explore these relationships for different tips and so forth. So if I move on, I kind of grab this slide, these images, these backgrounds from this book that I've kind of put here. Two great reference book that I highly recommend to go and read for much more in-depth technical details, and in terms of not only indentation technique, but in brief, Oliver Farr method. If I start from the far left graph, you have basically a Berkovich indenter, let's say, is pressing against an hard object, and again, all the parameters are defined. I'm not going to go very much in depth in here, but in principle, you have your loading and unloading curve here. You have load versus displacement. There is no hold time here. For biological tissue, we usually have a hold time to address creep behavior. But basically, Oliver Farr method is estimating the elastic modulus of that material based on the unloading curve from on the return phase. And you can see the dp over dh, that slope is what is estimated, where we are estimating basically the elastic modulus of that material. Again, please do have a look at these books. Lots of details. I'm not going to go into various terms there, but it's equally important to understand and appreciate how these calculations are happening. Let me move on to the first application, the first area on craniofacial growth, and tell you a little bit about our story in this area. So the real question for us a few years ago was whether we can use computer simulations to predict calvarial growth. And you can see you have here MRI and CT scan images of mouse at different stages during the development. P stand for postnatal day 7, think you have 14, 21, 28, and you can see how the brain is growing, expanding, and the whole craniofacial system is just expanding. You can obviously see how bone forming, the kind of yellowish areas gradually appearing. So the question that we were asking was, can we model this phenomena? Can we model a craniofacial growth? And why are we interested in this? Is because some conditions that are happening in human caused by, for example, early fusion of cranial joints. And treatment of this condition has been much debated in the literature, and the idea was to use these simulations to optimize treatment of this condition. So this is kind of a summary of what I just mentioned. So that we're thinking to use finite element method to model craniofacial growth. You can see a mouse model of this condition. The image in the middle is just trying to highlight the clinical condition. As I mentioned, is caused by early fusion of these cranial joints in our skulls, that then cause abnormal head shape, and these children need to go and obviously have surgical operations, and then that is really the point. And then there are lots of different surgical options are available. Which one is the best technique? How can we optimize and come up with the better techniques and so forth? Were basically the whole idea behind this project. Well, our starting point was to, really the plan of this research effectively was here. So we are planning to characterize normal and craniosynostotic mice skull growth, because we had nice data series of how skull morphology changes, predict craniofacial growth in normal and craniosynostotic mice, displaying this condition, do the same in basically human, and then move to patients, and then comparing different techniques. So this has been a project that started from about 2013 in my group, and is still ongoing, more towards the comparison between different techniques. So, but I'm just going to the indentation, as you can see, is kind of coming right early on. Very interesting in the characterizing these different mice. And why was that? Because this material property is just such an important parameter for this finite element simulation. So our journey started by characterizing the morphological changes in mice, and we have strong data series at different time point, at postnatal day 1, 3, all the way up to 42. This was just a solid baseline for later on comparison of our prediction of skull morphology versus this CD data. We could already see the differences that we are expecting between a normal growth in mouse and a abnormal growth. Having characterized the morphological differences, basically to then compare our finite element prediction against a reference point, key input, as I said, for this simulation were the material properties, and these properties were not available in the literature. And we basically started by characterizing the properties at different time points during the development. So we collected animals at the postnatal day 10 and 20. Postnatal day 10 in mouse kind of development correspond to about 1 year of age in human, and a postnatal day 20 is let's say an early adulthood or a teenager in our kind of development. So yes, 5 animals at postnatal day 10, wild type and mutant. You can see that the samples that we had, and the idea was to characterize the properties. We knew that there is going to be variation depending on where we are carrying the indentation, and we are trying to be as consistent as we can. Sample preparation, as I said, was important. So we collected fresh specimens right after the animals were called. The samples were preserved and in freezer, and then we basically went through a process of potting the specimens, aligning, make sure that they all have this alignment, same alignment, and then we basically indented in this dashed line that I've called it goes through the frontal bone and the parietal bone slightly further back. And you can see the sections here, how the sections look like. The idea was to quantify properties of these two different regions. This is basically forming the calvarial part of our skull, and the frontal is basically the forehead in human terms. So we measure bone properties and soft tissues. All indentation was basically carried out using a Berkovich tip. I think the details of bone indentations are here. We run this basically displacement control of 2.5 micron at 120 millinewton per minute, following by whole phase and then unloading. I haven't included details for exact indentation details of the soft tissues that are present between these bones, i.e. cranial joints. So, this is a section of mouse at postnatal day 20. You can see that you have this joint, the sagittal suture is basically this joint in the midline. We have been basically indenting throughout this whole cross section. You can see how this elastic modulus changes gradually from about 4 to 6 gigapascal, gradually goes up as we are moving from the midline laterally. That's kind of very well in line with what we know, that bone kind of forms during the development from the sutures gradually at the edges of these sutures. So this is kind of an old bone, more mature bone, and this is a kind of points 1 to 10 is much more younger. So having a lower elastic modulus kind of correspond to what we knew from the system. Obviously, bone is an isotropic material, and we knew that this variation is going to exist not only in this plane but also in if we are cutting this specimen in a sagittal section. So comparing, you are just looking at the coronal section here and the sagittal section. And again, you can see the variation that as you are approaching this joint, you can see how the elastic modulus gradually decreases from about 12 gigapascal to about 8 gigapascal close to the joint, and then gradually increases back up. And that again makes sense because there is going to be tissue differentiations that are happening over time. So bringing all the data together, I mean, these are all wild type animals. You can see the differences that we observe into the properties of the frontal bone versus the parietal bone. In the wild type group, frontal was gradually showing higher elastic modulus. P70, we had just one specimen, but what we were basically looking for was this gradient of how does what is the rate of bone formation. So the graph that you have here on the left hand side is kind of giving us a hint of rate of bone formation or changes in elastic modulus of the bone over time during the development. And this was very important for us to then build our finite element models and kind of model this tissue differentiation that happens across these sutures. On the right-hand side, you can see us trying to measure the properties of the cranial joints at different time point. At postnatal day 70, some of these joints are fused, so we couldn't measure, for example, the joint, the posterior frontal, this joint in the forehead. The properties that we are measuring were highly sensitive. The standard deviations are huge here. Not surprising, knowing that how sensitive and how challenging it is to characterize properties of soft tissues that are kind of embedded within hard tissue. We were basically measuring something in the range of 30 megapascal for the sutures, and it was interesting that that was kind of in line with some tensile testing studies that was carried out, for example, on rat and mouse of the same kind of joints. So let me move on. This is just comparing our wild type versus our mutant, and the differences between two were fascinating for us. And one major difference that we could see was in the properties of the frontal between the wild type, between a normal mouse and the mouse model that has this condition called craniosynostosis. And when we were already indenting, we could already see the differences in the morphology of the bone. You are looking here, comparing the wild type versus the mutant type, and you can see the kind of this porosity of this mutant bone at the earliest stages that was kind of gradually catching up and looking more like the wild type bone over time. The top 4 images are showing the frontal, the bottom 4 are showing the parietal. No clear difference, at least as far as you're looking at these bones under microscope, between the two for the parietal, but clear differences in terms of the porosity, as I mentioned, between the wild type and mutant at the frontal bone. Let me move on. I'm conscious of time, so this was just to highlight the thickening of the bone that we could see during the development, again, from, let's say, about 30 micron at postnatal day 20 to 50, 60 micron at P20, and then you can see this, how thickness is gradually increases during development. And for me to just kind of give you a quick overview of where this led us, was then basically we were included those properties into our finite element simulations. The gradient gave us an insight into the changes in elastic modulus and enabled us to model tissue differentiation across the sutures. And we were then basically modeling calvarial growth in mouse, including tissue differentiations. And we could see a good match between our predictions here in different colors you can see here, as well as the ex vivo data that we had. So we're pleased with this. It has its own limitations, but we basically moved on and translated this work into predicting calvarial growth in human, in the kind of same equivalent time frame up to 1 year of age, and that again translating that tissue differentiation in mouse to human. And now Connor, one of the students in the group, is just moving on to the phase of comparing different reconstruction techniques for treatment of one form of this condition called sagittal synostosis, caused by early fusion of the midline suture. And this is just some preliminary result where we are basically able to comment on the contact pressure that is on intracranial volume, or the brain is experiencing during the growth when you're comparing these different techniques. Some fascinating work is still ongoing, but it was just to highlight the importance of that characterization to then enable all these finite element simulation. But nonetheless itself, there were some interesting findings when we were doing the mouse work as well. So I'm going to move to the next topic on characterizing calcified tissue within the skin. Well, what is this? I mean, our skin doesn't have calcified tissue, but this calcified tissue are called basically osteoderms, and you see them in crocodiles, in turtles, and you see them in lizards. And we have been fascinated by by this in lizards, because lizards just simply show a remarkable diversity in the shape and morphology and of this calcified tissue within their skins, that we don't really understand what is causing it. So this is a completely different project compared to what I discussed earlier. The earlier project has developmental questions, whereas this project has more evolutionary questions as to what drives this diversity in osteoderms in reptiles, and where that can go then it's to enable us to develop various biomimetic or bio-inspired structures and devices and so forth, having learned from this remarkable diversity in nature. Yes, this is the kind of diversity that I was mentioning. These are a couple of images of different lizards. If you kind of scratch these surfaces and CT scan is a species, then you can see how their skulls look like, and this calcified tissue. I don't know to what extent you can see in this image, but some cases are overlapping, in some cases are very much flat, some cases hemispherical shape with different density. And what is remarkable is that some of these lizards have this on their part of their body, some have it on their entire body, and even within the same group, you see that diversity, that one specific species doesn't have any of these osteoderms and the other one has it all over their body. So this is part of an ongoing project. Some of the work that I'm going to share with you are still not published. This is a joint collaboration between 4 labs. My lab is basically looking into biomechanics of this using various characterization techniques, computational techniques. We have colleagues who are looking into the genetics and developments of this, and colleagues who are looking into functional aspects of this using in vivo experiments. So on our aspects, what we have, what I'm sharing with you right now is characterization that we have done on 3 species. We have done a good 5-6 species already, but I'm just giving a subset of that to date. So these are the 3 species that we have been focusing on, at least for the purpose of this talk. This is basically called Crucia, Hyladerma, and we have Physaurus on the bottom. It's kind of a snake-like lizard, but it's still lizard. Don't ask me why, but they call this lizard, trust me. So we have been collecting pieces of skin from these species. You can see already the X-ray plate images of this and overlapping osteoderms in Crucia, kind of mosaic hemispherical, let's say, in Hyladerma, and plates that you can see kind of a compound complex osteoderms in Physaurus. Have carried out histological sectioning of these species, and we can already see from this sectioning that there are some different regions. When you are staining these tissues, then you get different you appreciate differences within this tissue. You can see this is the osteoderm, this is the calcified tissue within the skin, and you can see this region that is highlighted in white, and the remaining part of it just give you some signal that these are 2 different tissues. So really the indentation technique could tell us, okay, we know that these 2 are different. Histology is giving us that signal, but what is the difference in the inherent mechanical properties of this tissue? So, and that kind of was on our side to then go and indent these osteoderms. So So you're looking at the section of these osteoderms. The osteoderms were obviously potted, indented, and characterized using a Berkovich tip. What you are looking at here is kind of, you see that this Ophisaurus, if you're the values that you are here are just basically elastic modulus that are measured. You can see the indentation on some of these images, but what is kind of fascinating for us, I mean, there are various fascinating stuff here. One is that this capping tissue that we have here is present in all these 3 species. You can see, and this is kind of matching our histological sectioning. And we can just see the variation in the properties of these tiny osteoderms, and why is that variation there? What drives it? What are the selective advantage of this? Well, there are ideas that these are protective tissues that are protecting the internal organs. But then why is it different in this species as opposed to the other species? So you can see that we are measuring something in the range of 30 to 40 gigapascal on the surface, and as we're going down, dropping to kind of half of that. And that is obviously a compound effect of, could be due to the nature of these different tissues or how these are organized within this kind of middle region. We think that it's kind of a mix of both, but yes, if it's fascinating that in some other species we don't even have this hard region, and what we see is that very much similar to what we are seeing in this middle region. Anyway, if I move on from this, the other question was on how similar are those properties to the properties of bone. So we are then indenting section of the bone that is immediate to these osteoderms where they are sitting. So osteoderms are sitting here on the very proximal surface, and then this is where I'm hovering over is basically a frontal bone underneath it, and this is the other species. The osteoderms are on the very surface, and then you have the bone, and where they are coming together, some are fused, some have a line. Again, remarkable diversity, and we see that what we are measuring is not on the capping tissue, but on the middle tissue is very much similar to the underlying bone. And the capping tissue is, the question for us was that, is this similar then to the capping tissue that we see on the teeth? So we have been indenting sections of mandible to then clarify and answer that question. And so these are sections of mandibles of these species, and the capping tissue that we are seeing in these species is effectively has same properties as the capping tissue that we have in our teeth, and it's just remarkable that these properties are present in different parts of the body of the same species. So the other bits of work that is going on here is around simulations of these osteoderms at a single level, simulation of these osteoderms across the whole skull, and understanding how they contribute to reinforce the overall structure of the skull, and what these different constitute of the single osteoderm. What do they do to the let's say overall stiffness of these osteoderms, either as a single osteoderm or as a sheet. And you can see that those indentation parameters again playing a key role in developing these finite element models. Where we have gone with this is that we have characterized it and designed biomimetic osteoderms, and are developing biomimetic sheets of osteoderms and trying to compare and understand the selective advantages of these sheets under, for example, impact testing. So that's really the story, or some of the story on the second project, and some other applications are that I haven't gone through here is we have been using indentation technique to characterize properties of thin films and thin biodegradable films that are promoting angiogenesis. There is ongoing work on characterizing properties of various scaffolds using for tissue engineering applications. This is a bioindentor with a spherical tip characterizing properties of a hydrogel, and titanium scaffold is shown here on the non-indentor system, and various other works. There is a simply remarkable body of work on characterization of various tissues, tibia, femur, mouse models, cartilage. It's just remarkable the advances that this technique has made this whole field of biomedical engineering. And I hope that I was able to show you some interesting examples of this technique and how it has fitted and enabled our wider research. So in summary, if I were to conclude, is a very powerful characterization technique. But remember, as with any other technique, it has various input parameters, and it's crucial to understand the impact of those input parameters on your output measurements. Lots of studies that I didn't go through that have been comparing different indenter tips, the effect of hydration, no hydration, various input parameters on this technique. And really, I think the baseline idea is that if you are consistent and throughout, then you can compare the differences between the structures that you are interested in. So with that, I'm going to thank various colleagues that have been contributing this work, and various funding bodies that have been supporting my group over years. So I'm going to leave it here, and thank you all for bearing with me, and I hope that you have found this informative. I'm going to hand at this point to Tauhid, and then I'll come back to take on any questions that you may have. Thank you.
Very much, Dr. Mehran. So what we'll do at this point is I'll hand over to our sponsors for today's webinar, Nishal Malde, Dr. Nishal Malde from Anton Par, and they'll give a quick talk and a video regarding their instruments and their company. Nish, over to yourself.
Great, thank you, Thavid. Firstly, look, a fantastic presentation insight from Dr. Moran on the work I've done on biological tissues and bone. It's really, really fascinating, and it's great to see how mechanical testing is going in towards fundamental research in terms of bioengineering and biomaterials. So my name is Nishal Malde. I'm a product manager at Anton Par, based here in the UK. And I just wanted to give you a little bit of a brief outline in terms of what kind of solutions that Anton Par can provide to you and your research and development, whether it's in academia or industry, to characterize material surface properties. Let me just quickly start. So Anton Par is a very well-established instrumentation manufacturer. In actual fact, I think next year we're going to be celebrating our 100th year anniversary. We've always started from the fundamentals of engineering, and we progressed into scientific instrumentation, and providing solutions for various applications and industries, and work towards research and development. We're more or less, I mean, this sheet's slightly out of date. We're probably around about just under 4,000 employees worldwide. So, we've got around about 31, 34 offices worldwide. So there's always an Anton Par office or representative close to you. But the biggest point I want to draw on this particular slide is that 20% of our revenue goes back into investment and research and development of new instrumentation, new techniques. And that all comes from evolution, from discussing with the scientific community, whether it's in industry or academia, what is missing. And from that, we take the next step in terms of development and the realization of new instrument techniques and new instruments that are becoming more powerful and widely used globally. So, I mean, what kind of applications do we kind of work with? Well, to be honest, I mean, this is just a very short selection. But, you know, if you're working within, coatings, thin films, wafers, polymers, fibers, membranes, glasses, metallics, and we just spoke about, tissue material, bones, cartilage, biomaterials. We cover that whole range of kind of applications if you're looking at in terms of understanding the fundamentals of surface properties. And what are the properties that we can measure? Well, look, I'm not going to go through every single point, but here, Moran talked about, hardness, elastic modulus, but everything from creep, stress strain, fracture toughness, coating adhesion, if you're working on specific coating, scratch resistance, coefficient of friction, if you're looking at tribological properties, wear, effects of lubrication, all the way down to even looking at nanostructure analysis as well, and down to atomic fundamentals. Moran talked about AFM as well, and that's something that we specialize in as well. So in essence, we are positioned in a way that we can provide a whole suite of scientific instrument solutions to help with your research and development, and hopefully that gives you a little bit of insight and understanding who Anton Parr are. And I'm going to hand over to Thavid to play a very short video. And thank you very much for your attention. I'd like to also thank other Surface Ventures for this opportunity. Thank you very much.
Great, thank you very much to Anton Parr and Nish. So at this point, we'd like to start taking some questions for Dr. Mehran. Should appear on the screen very soon.
Yes, so happy to take any question.
And the first question is, can we mount the samples in PMMA resin?
It's not something that I have, we have used, but equally, I think it might be possible. You need to just, I guess you can just give it a go and just see if it works or not. But I must say, our resin we haven't used PMMA for our sample mounting. Yes, so I'm not quite sure, but
Sure.
Yeah.
Great. We'll move on to the next question. How can we get the nano-indentation of human samples for FEA as it's the most difficult to get samples. Any extrapolation from similar animals is possible?
Well, sure. I mean, that's effectively what we have done here in the case of first example that I gave. If you remember, I was just talking that we are characterizing properties of a mouse skull and then extrapolating that basically to human. So the way that we were doing that there was just to find kind of comparable ages between mouse and human, and then estimating what are these properties look like in human. Obtaining cadaveric human tissue is obviously has its own challenges and requires its own regulatory approval framework compared to animal tissues. But it's doable. There is lots of work on cadaveric human tissue, non-indentation of cadaveric human tissue out there. But if you didn't find it for your particular application, then for sure you can kind of estimate properties based on testing in appropriate animal models.
Brilliant. Thank you very much for that. And that's the questions. That's all the questions for now. So we appreciate your time. So on that note, thank you very much, Dr. Mehran, for this engaging talk. We really appreciate you sharing. It's really appreciated. I would like to also thank Anton Parr and the Institute of Engineering and Technology for supporting this webinar. And a reminder, please do visit our website, as it will give you updates on our next speakers and previous videos of our previous talks. We will aim to organize our next webinar on the 22nd of July at 2 p.m. by Professor Alan Matthews. And the topic is on publishing in the surface engineering field, and that's sponsored by Amber Wright. So stay tuned for that. We'll also be having a third workshop in our tribology and surface engineering series, and that's on surface characterization. And that's with an optical profile and nano-indenter demonstration. And that's on the 8th of July at 9 a.m. and that's supported by Brooker. So we also ask for your support to take the time to advertise these lectures to your contacts if you find them useful. Hopefully others will too. So on that note, we would like to thank you again for joining us, and we hope you enjoy the rest of the day, and hopefully we see you soon. So thank you very much for your time, everyone. Thank you, Professor.
Bye.